Welcome to Lesson 8. This is probably my favorite lesson in all of Physics 12, just because it brings everything together so wonderfully. There are 2 examples we're going to do. That's it, and it's going to be great. So let's get right into it. First example. At the top of a 12 centimeter radius loop, we have a 350 gram toy car experiencing a force from the track of 2 newtons. Assuming that the car is released from rest and the track is frictionless, we want to determine 2 things. First, the height it was released from and the range it travels after leaving the ramp. There is so much going on here. It's awesome. So, the first thing to do is to identify what different parts are happening, or what different concepts are happening in different parts of each question. Obviously, this section over here is projectile motion. So we're going to have to reach back to Chapter 1, or Unit 1, rather, to look at that particular piece. We've obviously got circular motion here. We've got an object dropping, so we have energy. But what else? We've got it drops, it loops, so energy, circular motion, and then back up again. There's actually going to be a section right here of energy again that we have to consider. Energy right here. And the question for each one of these pieces is, where does each one start and end? Projectile motion obviously is right there. This little section of energy, obviously, right here. We've got this guy rising from level up to some height. But it's these first couple here that make this thing rather interesting. Using the information that we've got here, what do we do? We know it started up here, this little cart. It shot down the ramp and it looped up. We don't know anything about the bottom of the loop, but we do know we have a lot of information right here. And so, believe it or not, it's actually going to be right here that we're going to consult or consider the energy portion. Again, if you remember, energy doesn't care about what happens in the middle. It's only about the beginning and at the end. So the fact that this thing goes through a loop doesn't actually matter. We just know that it's going to be some height above the ground here. Circular motion is the piece that we're going to need here. You'll see why. We're going to use energy over here, and believe it or not, I misdrew. We're going to use this piece for energy here as well. So let's take a look at all of this kind of working together. So equation for the first one, I'll just write out the energy equation. We have energy initial plus work equals energy final. And now let's go back and look at the question. We're told that the track is frictionless right there. So the implication there is that work is equal to 0. We are told that the car is released from rest. So initially, all it has is potential energy. So we're going to get potential energy initial, and that's going to equal, now if we take it all the way to here, to this point, we're going to have potential energy at the end. Because we want this whole height here, we're actually going to call this height equals 0. So there's going to be some potential energy here and here. So our potential energy at the end plus kinetic energy. Oh, KE final rather. So we're going to have mgh initial equals mgh final plus 1/2 mv squared. And now let's see what we can do here. We can make this a little bit nicer because there's this same mass in every term on both sides. So if I divide both sides by m, it's going to cancel here, and it's going to cancel out in both of those terms. So we're going to get GHI equals GHF plus 1/2 v squared. We know what g is. G is 9.8. We're looking for the initial height here. We know actually the height of this guy, believe it or not, because we are told that this track has a 12 centimeter radius loop, which means the distance from here to here is 0.12 meters. Well, that also means the distance from here to here is 0.12 meters. So this is actually going to give us the final height of our object. So if you've got everything except for v squared, we have or we're looking for the initial height, we've got the final height, we need v squared here. We need to know how fast this object is going around that circle. And well, for that, we use circular motion. So we're going to need two equations here. F net c equals mac, and we're also going to need ac equals v squared over r. Now, this is not a gravitation question. This is a toy car going around a loop. So we have to consider what forces are acting on this guy here. He's on the inside of the track, so he's going to have an Fn pushing in, and he's going to have an Fg down as well. So for F net, we're going to have Fg plus Fn equals mv squared over r, and this v is going to be the speed of the car at that point right there, which will then slide in here. So we know Fg. Fg equals mg, and we are told the car weighs 350 grams, so mg is going to be 0.35 times 9.8. We're told that the car experiences, there's that piece there, we're told that the car experiences a force from the track of 2 newtons, right there. So it's going to be that plus 2 equals 0.35 v squared over, and now the radius of the loop is 0.12 meters. If you solve this for v, multiply here, add there, multiply that up, multiply that down, and square root, you're going to find that v is equal to 1.36 meters per second. Not very fast, and then that's going to slide up in there. We can finish this part of the question and say, okay, well, g is 9.8. I'm looking for the initial height, and that's going to be 9.8. The final height is 0.24 meters plus 1/2 1.36 squared. You solve that for the initial height. HI equals 0.33 meters, so 33 centimeters. Not very big. It's a little Hot Wheels car. The work, I think the work is relatively simple, but it's being able to identify all of the implications behind the pictures and the wording in the question that make this thing a little bit more challenging. So now let's jump over to here. We want to know, so it's come around, it's done the loop, it's launched off this thing here, we want to know how far it's going to go. The one thing we don't know is what the speed is here of the jump, and so that's what we're going to use the energy piece for. Now I said that the energy was from either the top or the, I said the energy piece, I originally labeled it here, and then I said actually we're going to jump it to it from here. You can actually go from either here or at the very beginning. It depends on which you want to do. Well, I drew it there, and I'm going to draw it to here. There's a whole bunch of implications about each piece. If we take the energy starting right here, we don't know what the velocity is at this point, but we know that height is 0. If you take this energy section starting from here, this thing's going to have some velocity. We know what it is. It's this 1.36 that we looked at, and it has some initial height above the ground already. Or if we go all the way back to the beginning, we know that the initial energy, the kinetic energy is 0, and it's got some maximum height here. So it doesn't actually matter where we start this thing from. For the sake of this question, I'm going to go from right here to right here to figure out what the speed is of that car. So for this section here, we know to start, it has potential energy. It's also moving at that point, so it has kinetic energy at that point, and that's going to equal, here it has some height, so so potential energy, final, and it's going to have some kinetic energy. Ke final. So let's run this through. The potential energy, again, this is not gravitation, this is just standard stuff. It's going to be mgh initial plus 1/2 mv initial squared equals mgh final plus half mv squared final. There's masses in every term, so they're gone. They cancel. So we're going to get g is 9.8. The initial height is 0.24 plus 1/2. We know the velocity at this point that we're calling the initial now for the energy section was 1.36. 36 squared, and that's going to equal 9.8. The final height here is 6 centimeters. So 0.06 meters plus 1/2 v final squared. So we've got all this going on. If you solve this thing for v, we're going to see that the v final, as this thing leaves the ramp, is 2.3 meters per second. And now this becomes a projectile motion problem. Let's do that section in pink. I'm just going to slide this down here. I'm going to redraw the problem. We've got the ramp. We've got the buggy at the edge of the ramp. It has a launch velocity of 2.3 meters per second. We know, based on the picture, that this is 0.06 meters, or 6 centimeters. And it's getting launched at 30 degrees. And that somewhere over here, it's going to hit the ground. And so what we're trying to find here is the range using an initial velocity at some angle and some height. This is the type of problem that we've already seen. So we're going to split this thing up into components, as we did before. We're going to have x and y. This guy, velocity is going off that way, so I've got that guy there, and this guy here. This is Vx, here is Vy, that angle there is 30 degrees. So we've got Vx is going to be equal to 2.3 cos 30. Vy is equal to 2.3 sine 30. That says this is a 90, doesn't look like it, but this should be a 90 degree angle. So that's going to give me a Vx of, I believe it's 2 meters per second, and a Vy of 1.15 meters per second. The distance we're looking for here is r, and we need some sort of time t. We don't know what time t is. Time t is the time it takes to get from here to here, which is the same amount of time it takes to get from here to here with that jump, the time to drop. And so we're going to go over here again, if you remember, to find ty. We need a, again, acceleration is downward, so it's negative 9.8 meters per second squared. And we know that the displacement downwards, I'm just going to go straight from beginning to end of from the jump to the end. And so I'm going to use the d is negative 0.06. That looks like a g, but it's supposed to be a 6. So what this means is I'm going to use this equation here. D equals VIT plus 1/2 AT squared. At this point, you should all be comfortable with the quadratic equation. So my displacement is downwards 6 centimeters, so it's negative 0.06 equals my initial velocity in the y direction of 1.15 t plus 1/2 negative 9.8 t squared. If I rearrange this equation, I am going to get the following quadratic. I'm going to multiply these together and move him over. So we're going to get 4.9 t squared minus 1.15 t minus 0.06 equals 0. And now at this point, I believe you all should have the mathematical ability to solve this problem. Quadratic formula, you saw on your formula sheet, negative b plus or minus the square root of b squared minus 4ac all over 2a. If you don't remember that, go back and take a look at it. We're going to solve, I'll put it in here, negative b plus or minus square root of b squared minus 4ac all over 2a. This is, this is going to give you a positive and a negative solution. What you should take here is the positive one, and you're going to find that t equals 0.28 seconds. This time is this time, and in the x direction there is no acceleration, so d equals vx times t, and I'm going to get my range is equal to 2 times 0.28, which gives us a range r of 0.56 meters, and we're done, beginning to end. One of the most comprehensive questions, using every bit of the curriculum that we've looked at except momentum, which I guess we could have put here if we wanted to, and that would have been awesome, but we didn't. It's the first example we're going to look at. Okay, flip the page. Here we go. We're not going to look at 2. What we're going to look at is example number 3. And then this will be it for this chapter. So we've got a roller coaster, and the roller coaster barely makes it around a vertical loop of radius 4 meters. We want to find the normal force of a 50 kilogram, or the apparent weight, same thing, of a 50 kilogram person when the roller coaster returns to the bottom of the loop. So what have we got going on here? Well, we know this section of the question is circular motion. We've got some circular motion stuff going on here. The way the question is laid out, the implication there is that this is going to be an energy section. And this is the part of the class where I would say, well, can we? And your answer should be, well, no, we can't. We don't know the height of this, so we have no way of knowing anything about what's going on over here. So this portion of it is effectively useless. There's no way we can use anything here. So let's just start the circular motion stuff and see what we get. So we know that he's barely completing the loop. If he's barely completing the loop, the implication here is that Fn equals 0. So the only force pulling in on him is Fg. We know his mass is 50 kilograms, so the force of gravity downwards on him is going to have to be 490 newtons. This doesn't look like a lot, but let's start it. So we have at the top, I'm just going to identify this for reasons that will be clear in a sec. At the top, I've got F net C equals MAC. We know that A or AC equals V squared over R. And so we're going to have Fg is the only inward force equals mv squared over R. So I'm going to get 490 equals our mass, which is 50 times V squared over 4. And we're going to use this to figure out that the velocity equals 6.26 meters per second. That's neat. Doesn't do much for us at this point, but this is, using the information that we've got, this is one of the things that we can do. Let's jump to the bottom of the loop and see what's going on here. This guy's at the bottom of the loop, so Fg is still acting downwards, but it isn't causing the circular motion. It's the Fn upwards that is. And that's what we're looking for. So I'm going to go down here, and we're going to look at the bottom of the loop. We've got Fn, I'll start from the beginning. F net C equals MAC, and we've got AC equals V squared over R. So at this point, my net force here is going to be, remember, in a circle, inward is always positive. So this one's going to be Fn minus Fg, because Fg is acting downwards here, equals mv squared over r. Now, we don't know what Fn is. That's what we're looking for. We want to minus Fg, which we already know is 490. The mass is 50. The radius is 4. It's a circle. We already know it from the question. We just need to know how fast he's going at the bottom. So we know how fast he was going at the top. We don't know how fast he was going at the bottom. So what can we do here? Well, the thing that you need to recognize here is that he was up, moving slowish, and now he's at the bottom. And the implication here at the bottom is that he's probably going to be moving faster. If you're going from a height to a bottom, and you're dropping, and you want to know what speed you're going, you're going to have to use energy here. So this is where the energy part of the problem comes in. This is the initial state. This is the final state, and we want to take a look at how the energy is changing from top to bottom. So let's do that. We're going to have energy initial plus work equals energy final. We are not told anything, I don't think, about the friction in the track. So because we are not told there is friction, we're going to assume that it's 0. At the top, if this is the initial state, his potential energy is present and his kinetic energy is present. Okay, sorry, let's continue. Energy. We've got potential energy, kinetic energy at the top, and kinetic energy at the bottom. So PE initial plus KE initial equals KE final. We're going to have mgh initial plus half mv squared initial equals half mv squared final. My masses cancel because there's mass in every term. And so I'm going to get 9.8. It's a 4-meter radius. So the height above the ground is 8 meters. So 9.8 times 8 plus 1/2. We know the velocity at the top is 6.26 meters per second. Square that, and that's going to equal half V final squared. If you solve this thing for V final, what you're going to see is that V final is equal to 14 meters per second. So I can shove that in there and find Fn. So Fn is going to equal 50 times 14 squared over 4 plus 490 equals 2,940 newtons. All the concepts coming together, and this is where the questions can get really quite tricky because you have to be able to identify what goes where and when and how do we use all this information. And if you're not willing to start the problem, even if you can't see where it's going, just start with things and see what happens. So I want you to take a look at the following questions for your homework. I would like you to do number 1. I want you to do number 2. I want you to do number 8. I want you to do number 10. And that's it for this lesson. There are 2 more questions I want you to take a look at though as well. I want you to do 4 and 5. These guys are review. So that's your homework 1, 2, 8, 10, 4, and 5. As always, comments, questions, concerns, please feel free to fire me an email or come to my office hours.